Okay, so today we are going to start with the states of matter. So we know there are three states that we usually discuss, which are gases, liquids, and solids, right? So first we talk about
Yes, sir.
gases. So think of a gas which is enclosed in a container as you are observing in this diagram. So what gas molecules usually do, how they move?
They collide with each other on the walls.
Yeah, they actually moving randomly, and as a result of that random movement, they collide with each other and they collide with the walls of the container as well, right?
Yes, sir.
So what happens that when they collide with the walls of each other and bounce back, so that collision actually, obviously, if they are colliding with the walls, they are putting some force to the specific area of that wall.
Yes, sir.
So if you recall this expression, that force of over area is equals to
Pressure.
pressure. So from here, the pressure originates that when they collide with the walls of the container and they are colliding with each other as well, this results in the formation of pressure, and that is how a gas molecules exert the pressure. And we call that pressure a gas pressure. If you have any confusion in this, please ask.
No, sir.
Okay. Now, there are two things we have to discuss over here. First is what happens when we change the volume. So see, obviously, if the container is this much, and if, for example, if I take a bigger container, so these molecules do the same thing, but now as the container is a big enough, so the molecules
The
are
pressure
traveling
is
up.
decreased
How?
because they are more spread out.
They more spread out, so the frequency of the collision actually decreases, right?
Yes, sir.
And the pressure decrease. In the other words, for example, if I decrease the pressure, if I take the smaller container, the particles comes closer to each other. And as a result,
Yes, the frequency
frequency,
increases.
the frequency increases
Pressure increases.
and the pressure increases. So we can say that at a constant temperature, the volume and the pressure are inversely proportional to each other, right?
Yes, sir.
Okay. So when we increase the pressure, when the volume is increased, pressure gets lower, and when the volume is decreased, pressure gets more.
Increase.
Yeah. So here there is a, uh, visual representation and the graph. See, volume is proportional to the reciprocal of pressure, right?
Yes, sir.
So it means if I plot volume against a reciprocal of a pressure, that is 1 over pressure, so I'm going to get the straight line.
Yes, sir.
Okay. And instead, if here it's a pressure, so I'm going to get a line like this.
Yes, with a decreasing gradient.
Yeah. And it is not, linear. Remember, it is always in a curved shape if there is a pressure over here. Okay.
Yes, sir.
Okay. Now changing the gas temperature. So if we keep the volume, or you can say the pressure same. No, if we keep the volume same and we increases the temperature, what happens that there will be a more kinetic energy. So the particles start moving
Yes.
faster and they will do more
Yeah.
frequent collision, which results in the increase in temperature. Oh, sorry, which results in the increase in pressure. So temperature is directly proportional to the pressure at constant volume.
Yes, sir.
See over here, that is a visual and a graphical representation. When the temperature is increased, they becomes more faster, and as a result, they will colliding more frequently, which leads to increase in the greater pressure. Okay. Now, we have a kinetic theory of a gases. Okay, actually, this whole theory was there till I think 2021 exams. And since 2022 onwards, the whole theory is not now included. So I'm going to mark the things which are not in the syllabus now.
Okay.
Okay. So this theory says that the gas molecules are in a continuous motion. They are moving fast and randomly. The second thing that this theory states that the volume of the gas molecules is negligible. It means their volume of a gas molecules is zero. Okay.
Yes, sir.
Third, there is a no attraction or repulsion between the gas molecules. So it means they are saying that if the gas molecules are there, as we have discussed previously, that the gas molecule there are molecules, there is a intermolecular forces of attraction between the molecules, right?
Yes, sir.
So, but they are saying that the kinetic theory says that if the molecules are of gas, that there will be no intermolecular forces. And the collision between the gas molecules is elastic, which means that on colliding, they do not lose kinetic energy. And the temperature of the gas is related to average kinetic energy of the molecules. Okay.
Okay.
So any gas which follows this kinetic theory, we call those gases the ideal gas.
Okay.
Okay. Okay. From this thing, this is not now the part of the syllabus, but you have to know that in reality, the gases do not follow the kinetic theory, and which gases which do not follow the kinetic theory, we call them real gases. Okay, so the
Okay, sir.
ideal gases
Yeah.
are ones which behaves like this, which follow all these points, and any gas which do not follow any of the point is called a real gas. Okay,
Okay, sir.
any confusion till here?
No.
Okay. Now, when we talk about the ideal gas, so the volume of the ideal gas basically depends upon the pressure and the temperature. If you increases the temperature, what will happen? The particles collide more frequently, and it leads to
Yes.
increase in the pressure, right? And if we changes the
Yes, sir.
volume, the pressure would also change inversely. But here, what we are going to see, this third point, at constant pressure, if the volume of the gas increases by increasing its temperature because of because of the kinetic energy of molecules. So what they are saying, if we increase the temperature and this would be the condition, at this specific condition, if we increase the temperature, the volume of the gas also increases. And if we decrease the temperature, the volume of the gas also decreases. See over here, this is the visual representation. There is a low temperature, and now see it is a movable piston to make sure that the pressure remains same. So when we increase the temperature, molecules start colliding more frequently, and as a result, they are hitting this wall more frequently, which results in the expansion, and as a result, the volume decreases because the pressure is constant. Is this clear?
Yes, sir.
If you have any query till
The
here,
volume increases.
sorry.
The volume increases
The
when there is
volume
an increase
increases.
in temperature.
Yes. Okay. Now, these are the limitations which are now not the part of the syllabus.
Okay.
Okay.
Yes, sir. So we just skip it all?
Sorry.
So we just skip it?
Yeah, because it's not, if you can check the syllabus file shared by the Cambridge before 2021, for 2021 examinations and the earlier, you are going to find this, but for 2022, 2023, and 2024, we don't have this. Okay, you are going to appear in 2024, right?
Yes, sir.
Yeah, it's
October.
mentioned, so that's fine. We now don't have this thing, okay? And this is also excluded now. So these
Okay.
are the three relations that we discussed earlier, right? And this equation
Yes,
we
sir.
in mode, this equation is also there. And this part is we already done that we can use this equation in two ways. If they ask you to find any of the value, we can use this how to use this equation. You have to remember that pressure is taken in pascals in this equation, volume is taken in meter cube, R is the general gas constant, which is 8.13 or 31, which value is always given. T is the temperature, which is always in Kelvin, and is the number of moles. And further, what we can do if we have to determine the molecular mass, MR, relative molecular mass, so we will open this moles into M over MR, and then make the MR subject to find the find the relative molecular mass of that gas. That's what we did it in moles, right?
Yes, sir.
Okay. Now, okay. So these points are also not needed now. Because these are not the part of the syllabus. Okay, now we have the next thing, the lattice structure. Okay, so
Yes, sir.
when we talk about the lattices, we initially categorize lattice structures into three types: the giant ionic lattices, covalent lattices, and the metallic lattices on the type of bonding they have, right?
Yes, sir.
Okay. So when we talk about the giant ionic lattices, we know that they have a giant structure and there are positively charged ions on alternate position in the lattice, and the ions are uniformly arranged, right?
Yes, sir.
When we talk about the metallic lattices, it is also a giant one, and it is a cations and the mobile electrons, and the cations are actually surrounded by those mobile electrons, right?
Yes, sir.
Okay. What are the rest of the properties of the giant ionic lattices? We did it in the chemical bonding, right?
Yes, sir.
Okay. Now, okay. Uh, okay, first I'm going to discuss the metallic one, then we will move towards the covalent one. Okay. So when we
Okay.
talk about metallic, they are strong and hard, insoluble in water. Otherwise, they do react in water like group 1 and group 2 metals, right?
Yes, sir.
But if the metal is not reacting, it stays insoluble, like you put a zinc, iron, gold, copper, titanium, anything in water, it doesn't react. So, and it stays in the solid state in water. So we say insoluble in water. They are free moving electrons are there. So they conduct heat and electricity, and they are malleable and ductile. With the yellow line over here, I have mentioned the reasons why they are strong and hard due to the strong attraction between the cations and the delocalized electron that makes them strong and hard. They conduct heat and electricity. So why they conduct electricity? Heat and electricity because they have a free moving electrons. Now they are malleable and ductile. So why they are malleable and ductile? Because of the because of the layers of cations can slide over each other. When we apply the force, the layers can slide, and which makes them malleable and ductile. Is this clear?
Yes, sir.
Okay. Then they have a high melting and boiling point. Okay. Okay. This is for giant covalent bonding. So when we talk about covalent lattices, covalent bonding results in the formation of molecules. So these molecules are of two types. One are simple molecular and the other one are giant molecular. So in the bonding, in the covalent bonding, the almost all the examples that we did earlier, like carbon dioxide, ethane, C2H6, C2H4, oxygen, carbon monoxide, ammonium, ammonia. There are so many examples, right? All of them are belongs
Yes.
to simple molecular structure. All the bonding, all the molecules, all the shapes, all the structures that we did in covalent bonding in the previous chapter. Okay.
Yes, sir.
So here I take three common specific examples of the simple molecules: water, iodine, and Buckminster fullerene, which is a molecule of 60 carbon atoms. Okay.
Okay.
When we talk about giant molecular, okay, their properties we also did in the chemical bonding, right?
Yes, sir.
We talk about the general properties of the of the simple
Yes,
molecule,
sir.
right? So their properties
Yes.
are also we are done with it. Now we have a giant molecular. In giant molecular structures, we have a graphite, diamond, and silicon oxide. Okay. Now let's talk about the properties of the giant molecular. Firstly, they have a very high melting and boiling point. That very high melting and boiling point is with the is also there in the ionic lattices and as well as in metallic ones. Okay. But the reason why the giant molecular have a high melting and boiling point, so its reason is that there is a large number of covalent bonds throughout the whole structure. So as a result, they need a very high, lot of energy to overcome those forces. But this point is valid for all of them. But whenever there is a comparison between, for example, diamond and graphite or silicon and graphite, then you have to mention this point as well, that graphite has a weak intermolecular forces between its layer. That's why graphite's melting point and the boiling point is relatively lower than the silicon and the diamond.
Okay, sir.
And beside this, you can also mention that if you have to compare graphite and diamond, so we will mention that in comparison, that diamond has a more number of covalent bonds in its lattice as compared to graphite, or graphite has a lesser number of covalent bonds as compared to diamond. That's why graphite's melting and boiling point is lower than that. Okay.
Okay, sir.
Now, when we talk about graphite is soft, and the reason is that these layers can slide over each other. There is a layered structure, and there are intermolecular forces which makes graphite soft. On the other hand, diamond and silicons are hard. It is because they have only a strong covalent bonds. Diamond and silicon dioxide, they doesn't have any, intermolecular forces. So they have only strong covalent bonds that makes them hard. Is this clear?
Yes, sir.
All of them are water insoluble, whether it's a graphite, diamond, or silicon dioxide. Graphite conducts electricity only due to free moving electrons. In graphite, diamond, carbon has a free moving electron. That's why graphite conducts electricity. And the reason is that, for example, if we look at carbon, carbon has a 4 electron in its valence shell, right?
Yes, sir.
So in diamond, carbon makes all 4 covalent bonds. But in graphite, as carbon has a, but carbon can make only 3 bonds and 1 electron of carbon stays unbonded, and this becomes the free electron. And this electron, this one free electron from each carbon atom can move freely on the whole layer, makes it the conductor of electricity. Is this understandable?
Yes, sir.
This is for diamond and this is for graphite. Okay, so graphite has a 1 free electron. Any confusion so far?
No, sir.
Okay, so these sometimes examiner asks you to show the lattice. For example, if examiner asks you this, so you have to show the lattice in this way for the ionic one. Okay.
Okay, sir.
So we have a lattice for sodium chloride and magnesium oxide. Now you can easily see that at alternate positions, if you see, we have a positively charged ions, right?
Yes, sir.
So that's what happens in ionic lattices. Okay. Now, see, these three examples we did for a simple cold molecular. So see what happens in the water. Now you can easily relate that this joining of the atoms are due to which bond?
Hydrogen bond.
No, this joining of the atoms in the molecule. It's a covalent bond, isn't it?
Yes, sir.
So see, it's a covalent bond, and see, the two molecules are attracting with each other, and that is due to the hydrogen bond.
Yes, sir.
Understandable?
Yes, sir.
Okay, so the Buckminster fullerene, which I have told you, C60, is a molecule of a 60 atoms which has a shape like football. And if the examiner asks you to define, so you can write that it has a ring-like structure and it has a two types of ring. Like one ring has a hexagonal ring, which has a 6 carbon atoms, and you can see in the figure the other ring is 5 carbon atoms, which is pentagonal. So that's what in its structure has. And if you see, these all are carbon atoms, right?
Yes, sir.
So how many bonds each
All
have?
of them,
Yes.
all of them have 3 bonds. So
Yeah.
one free electron.
One free electron. So it means it do conduct electricity, but it's a ball. So it's the electrons move in the ball only. So the conduction of the electricity is to a very lower extent to this molecule only.
Okay, sir.
Understandable?
Yes, sir.
Okay. Now, when we talk about iodine, iodine is diatomic, as we have discussed earlier. So first, a covalent bond is made, right? And this is the covalent bond over here. That's why the two atoms joining. Now you are seeing the lattice in the lattice. These lines are actually representing you the intermolecular forces between the iodine molecules. Is this understandable?
Yes, sir.
Okay. Now see, this is the structure of a graphite where there is a one layer, there is a second layer, there is a third layer. So this layer is continued till here and here, and the electron are free over here. So electron can move in this whole layer from one point to another point. That makes graphite a very good conductor. But over here, this gray Buckminster fullerene is not uh, good conductor as good graphite because the movement of the electron is actually limited to this football, okay, or this ball-like structure only. It is not going to move from the one end to the other end. Is this understandable?
Yes, sir.
Now you can see the diamond, and if you see in diamond there are all carbon atoms making 4 bonds, and there is a no intermolecular forces. As you can see, there are intermolecular forces over here in the form of dotted lines, right?
Yes, sir.
So it is more compact, that makes it even stronger. Here we have a silicon dioxide, SiO2. So you have to remember this, that in silicon dioxide, if you look at the silicon atom is getting bonded with the 4 oxygen atom. But each oxygen atom is getting bonded with only 2 silicon atoms. Okay.
Yes, sir.
So that's what you need to understand. Then this is the metallic lattice, because in metallic lattice we have all atoms are of a same kind, and between these atoms are actually cations, the electrons are moving freely, right?
Yes, sir.
And here is the demonstration of the malleability or the ductility. See, when the force is applied, these layers are actually gets pushed away, and as a result, it is shifted to the right side, making in the change in the shape of the metal. See,
Yes, sir.
is this understandable?
Yes, sir.
Okay. So here we are done with the chapter.
That's the chapter.
Yeah, that's the chapter.
Oh.
Actually, initially there was these things which takes a longer time, but now from 2022, they have excluded these, which makes this chapter even more smaller.
Okay.
Okay, so